This video is on the P-channel MOSFET, and more specifically on inversion. Structurally, what we have here is a P plus diffusion on one side and another P plus diffusion on the other, and between them is where we want to have a channel eventually. We also put an insulating oxide region here, and that's because we want to build a capacitor that connects from top of that region to the region immediately underneath that gate oxide. And that's what's going to induce current flow. So first let us talk about the concept of inversion. And basically what we're going to do is we're going to apply a negative voltage that is great enough over the threshold voltage to induce the action that we're looking to induce. So let us ground both sides of the channel, and let us apply a negative voltage to the gate. As an example, -1 volt. Well, we have a capacitor from the top to the region immediately underneath that gate oxide, and we also have a capacitor on the other side here. When we apply a negative voltage on the top, we're going to induce a negative voltage in that region there, and that negative voltage is going to attract positively charged holes from the source diffusion region on the left into the middle, and also from the source diffusion on the right into the middle here. That negative voltage is so high that it basically populates that middle region, that entire middle region. And what we've done here is that now we have a region between these two P plus regions. We've connected them with effectively a P-type region here. And what we've done is we've inverted a channel, because before we had no channel. This is N-type, but now we've made that region P-type, so we've inverted a channel that connects those two P plus diffusions, and it went from N to P, so that's an inversion. So in inversion, then we have a resistance between these two terminals, and that resistance is going to increase with length, is going to decrease with width, and that's if we make this device wider basically into the screen. What we see here is that now when we induce current flow, we can induce more current across that width. So it decreases the resistance the wider the channel is. This is the conductivity of holes, the ease with which holes move across a region, and the resistance is going to be inversely proportional to that ease. It's also inversely proportional to the gate oxide, because the gate oxide basically determines how much charge we can have underneath the channel. The larger the capacitor, the capacitance, the more charge we can collect in that region. And it's also inversely proportional to how much voltage we apply to induce that channel. So the more negative voltage we apply to that gate, the more charge we have, the lower the resistance, and that's what this entire term is saying. But just to make it make the numbers positive, instead of looking at just the gate voltage, we're going to look at the gate voltage with respect to the ground, and in this case to this voltage here. So if I remove markers here, since we apply a negative voltage to this terminal with respect to this terminal, when we look at this voltage difference from what we're going to call the source, and then explain why later, from the source to the gate is positive, and when we have that positive voltage is when we can induce a channel, as long as that positive voltage is greater than the effective threshold of the device. And all that means is that we have a great enough voltage to invert the channel. We can combine these two terms here, the mobility and the oxide capacitance, with what we call the transconductance parameter. That's just to shorten the expression. We can also combine these two terms here. We know that SG stands for the difference between source and gate voltage, so SGT is the difference between source gate voltage and threshold. This one on the bottom is useful because we call that gate drive. Basically, this is how much voltage we avail over the threshold voltage. So if the gate drive is 0, we have basically no current flow, or the resistance is infinity, and this is what this is saying. So, but we can take this one more step, and we can say that this whole thing here is describing the baseline resistivity of the device. And we call this the sheet resistance because this is the resistance of one square. And this right here is the number of squares. So when we look at the length over the width, how many widths do we have across that length? So if we have the equivalent of 10 widths across that length, that means that we have 10 squares. 10 squares times this sheet resistance, which is the resistance of one square, gives us the total resistance. So this is useful. Now let us talk about conduction. And triode refers to when the current is sensitive to both gate voltage and drain voltage. So basically all we're doing is applying a voltage across this channel here. So it's the voltage across that resistance. So we put the voltage here, and then this entire thing here is just 1 over the resistance. So we recognize the length that we had on the top expression, the width, the transconductance parameter, and the gate drive. But look at this here. This is a correcting term, and let us see what that is referring to here. So remember, we're going to ground this side. We're going to apply negative voltage here. But what we're saying here is that we can apply also a negative voltage here. So on the left-hand side, we have a large negative voltage, so we have a lot of charge underneath the gate oxide. On the right-hand side, we have less negative voltage, or lower negative voltage, so that we have less charge. With less charge, we have higher resistance and lower current. So that's what this is modeling here. When this voltage here, this drain voltage is negative, the source drain voltage is positive. When we apply a voltage there, we get a lower current. One way to think of this is that if you look, we can divide the device in two. The right half side basically connects to the right terminal, the left hand side connects to the left hand half terminal. And we're basically reducing the voltage across the gate oxide on the right half side. So this voltage here affects half the channel, so its effect is half here. But that's just a way of remembering. This is ultimately a correcting term that adjusts the resistance when we apply a voltage to the terminal all the way on the right. So we also have saturation, and that's when the current is insensitive to that terminal voltage. And basically what we're saying is that that terminal voltage is greater than some saturation level. Let us look at what we mean by that. So again, we can ground this side, we apply negative voltage here, and now we're applying also some sort of negative voltage on this hand side. The voltage across the gate on the left is very negative, so we have lots of charge here. But now what we're going to apply a voltage on the voltage on the right is going to be just the threshold level. And below the threshold level, we have no charge. At the threshold level, we basically have no charge, and that this is what this is saying. So the voltage across the oxide is basically just the threshold voltage there. And what we see there is that we've just pinched the channel. And we can rearrange this here and solve for the source drain voltage that does that, and that's the saturation voltage. So when we swap these two terminals, we get that the saturation voltage is a difference between source gate voltage and threshold voltage, which is the gate drive, SGT. What is interesting about this is okay, again, we ground this side and we apply negative voltage to the gate, but now we apply a very high negative voltage to the other terminal. And what we see here then is the point where the channel pinches, the voltage across the gate there is just at the threshold level because that's how it pinches. So that voltage there is just a saturation voltage. And this space here, it drops the difference between the saturation voltage and whatever voltage we apply to the right-hand terminal. What that means is when we look at the current is going to be still the voltage across the channel over the resistance, except that now the voltage across the channel is just the saturation voltage. So we have the same expression as before, except we're using the saturation voltage for VSD. One thing that we'll note here is that this right here is the gate drive. And we also know that VSD the saturation voltage is gate drive. So we have gate drive minus half a gate drive. That's half a gate drive times a gate drive is gate drive squared over 2. So that's what we see here, gate drive squared over 2. And then we can carry the width, we can carry the transconductance parameter. But notice this channel length here, we're not using that one anymore. We're not using the effective channel length. So I want to remove markers here to declutter the screen. The effective channel length is just the length of the channel to the pinching point. But this is not what we're using on this expression here. What we're going to use is the overall length, the physical length between the P plus diffusions. Okay, with the physical length, how do we basically correct for that difference? So that's what we have here on this hand side. We call this channel length modulation parameter because it's a parameter that models the effective variation in channel length. So when we have a higher source drain voltage, we have a shorter channel, which means lower resistance and higher current. So when we have a higher source drain voltage, then therefore we have a higher current. So this is how we model channel length modulation. Now let us remove markers again. In analog design, it's very useful to solve for the saturation voltage. And in analog design, we also often control what the current is. So we can take this term here and solve for it with respect to the current. So all we have to do is take the W over L and take it on to the other side. So it's ID over W over L, and that's what we see here, and we see ID. Multiply times 2, divide by the channel length modulation term, and divided by the transconductance parameter. And then the gate drive is squared, so we take the square root of both sides, and that's what we see here. One last thing here is that when we make the physical length much higher than the minimum length, so when the distance here from P plus diffusion to P plus diffusion is very high, then this variation in channel length is a very small fraction of the overall channel length. When it's a very small fraction, that means the variation in current is very low. And translating that to our channel length modulation parameter, it means that the channel length modulation parameter is very low, on the order of maybe 1%. So a lot of times we'll neglect this term here, and that's because as designers, we choose the length to be much greater than the minimum channel length. Now let us talk about the body effect, and let us remove markers here. So remember, we have a capacitor from the top to the bottom, and we also have to the channel, and we have a capacitor from the bottom or the body to the channel. So any variation in voltage at the gate will induce channel resistance variation. Well, the same thing from the bottom. So when we apply positive voltage to the body, we induce a positive voltage at the channel, and that will repel holes back. Repelling holes back is like increasing resistance, but in another way of modeling that is like increasing threshold. So this is the expression that we use to model that. So if we increase the body voltage here, we make this more negative. So this whole term here becomes positive. So this term is greater than this one, so that difference is positive, multiplied by just a constant. We add voltage to the effective threshold. This is just a modeling expression. So we're modeling the effect of the bottom gate through the threshold voltage. So when we apply a positive voltage here at the body, inducing more current flow by or reducing current flow by inducing a larger threshold voltage. But I'll say it more intuitively. Basically, we have a top gate here that controls the resistance, and we have a bottom gate that controls it very much the same way, except that the capacitances are different. One is an oxide capacitance, the other one is a depletion capacitance. Also note that instead of applying a positive voltage here, we can apply a negative voltage, and a negative voltage attracts holes into the channel, decreases resistance, and increases current flow, which is the same thing as saying decreasing the threshold voltage. And you go back to this expression. So if we put a negative voltage on this side, then this becomes a larger positive voltage, and this whole term becomes lower than this one, and then the correcting factor here, or the adjustment, is negative, and it reduces the effective threshold voltage from the original zero bias condition. So let us remove markers here, and what we have as a result here is these IV curves. So if we apply a source gate voltage that is greater than the threshold, we get a current that is largely insensitive to source drain voltage if the source drain voltage is higher than the saturation level. If we increase that source gate voltage, we get a higher current. When that source drain voltage decreases below the saturation level, we enter triode, and that's when the current becomes sensitive to source drain voltage. And if source drain voltage goes to zero, the voltage across the channel is zero, there's no current flow. Now, interestingly, if you look at the structure of this device, we can apply the ground to the right-hand side and a negative voltage to the gate and a negative voltage to the left-hand side. What we see here, all the voltages are reversed, but since the device is symmetrical, everything will work the same way, but in the opposite direction. So the current flows in the opposite direction. So what we see here is that if we take the source drain voltage and we make it negative, we're going to get current flow in the negative direction. And this current flow is going to be exactly the same, and it's a mirrored reflection of the first quadrant. So that's why we see these currents here are the same as these currents. Lastly, let's talk about the symbol here, and we're going to remove markers again. Notice that this P plus diffusion is providing all the positive charge carriers into the channel. So we call this the source terminal. Those charge carriers eventually leave out of the other terminal. So the other terminal, we call it the drain terminal. And current, since flows in the direction of holes, current is flowing into the source and out of the drain. So this is what we see here. Current is flowing into the source. We use an arrow and we use it on the side that is the source, the one that is providing all the charge carriers, and we point it in the direction of current flow, so it flows into the channel. Now we also have a capacitance from the top gate to the channel, and that's what we're drawing here, a capacitor from the top gate to the channel, and this capacitor is the one that induces a channel underneath it. This P-channel MOSFET is on top of an N-type body, and the N-type body here has also a connection, and it's on the opposite side of the channel. It's a capacitor on the opposite side. So we have a terminal here on the opposite side of the gate, and that's the body terminal. So here we have the source, the drain, gate, and the body terminal of the device. Well, I hope this was helpful. Thanks for watching.